All right, welcome to Etale Cohomology on October 29th, 2020. So last time we introduced the Kunneth formula. So we introduced cup product. So at the very end, I gave you a formula for the cup product on check cohomology and the Kunneth formula. So let me briefly recall what the cup product was, and then I'm going to give a kind of simpler. I'm going to recall the statement of the Kunneth formula, give you a slightly simpler formulation in good cases, and then sketch the proof. So first of all, let me just remind you what cup products were in check cohomology. So in check cohomology, they're given by the following formula. So it's enough to define a product from hi of the here we have x and y. Let's say our K schemes. And F and G are constructible sheaves. Well, let's even just say are just sheaves of Z mod L to the n Z modules is all we need for this. On X Etale and Y Etale respectively. So then, so given a cover U to X and V to Y, we can take the check complex of U over X with coefficients in F, take its cohomology, and tensor that with Hj of the check complex of V over Y, G. And then my claim is that there's a map to Hi plus J of the check complex of U cross V over X cross Y, and then I'll write just F box tensor G. So this box tensor means you pull back along one of the projections and pull back along the other projection and then tensor them together. Okay, and what is this? This actually comes from a map of complexes. So this comes from a map from the total complex of the check complex of U over X with coefficients in F, and then tensored with the check complex of V over Y, F to the check complex of U cross V over X cross Y, F boxed product G. Do you guys want me to say another word about what I mean by this box product, or are people familiar with it?
Could you say another word about the box product?
Sure, great. Yeah, so let me just say what that is. So we have X times Y. This maps to X and it maps to Y. We have some projections pi1 and pi2. And when I write F box tensor product G, what that means is you pull back through the first F through the first projection and pull back G through the second projection and tensor them together. Right, so this is a way of if you start with a sheaf on X and a sheaf on Y, you make a sheaf on X times Y. Does that help, Arvind?
Got it, thanks.
All right, so the most important example maybe is where F and G are the constant sheaves Z mod L to the NZ, and when you tensor them when you box tensor them together, you get Z mod L to the N, the constant sheaf Z mod L to the NZ. Okay, so what is this this product? So here given F, which is in Ci, sorry, the ith term of the check complex of F. So this is a section to the pullback of F to U cross U cross U cross U cross U I times over F, right? And given G in the check complex of V over Y, sorry, that should be a G. So this is a section to G pulled back to some multiple fiber product of V over Y. Well, what what do we get? So we get FG maps to what I'll call just F box tensor G in C I plus J U cross V over X cross Y. F box tensor G. And well, what is this thing? It's you just do the obvious thing. So here you have a n-tuple fiber product of U cross V over X cross Y that maps to the n-tuple fiber product of U over X and V over Y, and you just pull back these sections and tensor them together. Okay, so this is a very concrete operation in check cohomology. So the remark, and sorry I went through this so quickly at the end of last time. So the remark is that so check cohomology doesn't always compute derived functor cohomology, right? There's something to check here. I mean, you have to actually check that this gives you a morphism of complexes, which is not so obvious. Like you have to check that the differentials behave well. So you should check that. Good luck. It's not actually that bad. So the remark is that these sorts of cup products exist in sheaf cohomology in general. So in derived functor sheaf cohomology. But it's actually really non-trivial to make them. So if you want a reference, you should look at Iverson's book. So which does it for topological spaces, but the argument for sites is more or less the same. So it's really it's sort of not that easy to make these operations, but you can. Okay, so now let me state the kind of concrete, so the concrete form of Kunneth. So so let me give two statements. So one is suppose X and Y are proper varieties. Over K, and lambda is either Z mod L to the NZ or ZL. So meaning the ZL sheaf ZL. So the thing where what is a ZL sheaf? It's like an inverse system of Z mod L to the N sheaves, and you just take all of them to be the constant sheaf Z mod L to the NZ. So the statement is that if HI of X lambda or HI, sorry, let me say H star, or H star of Y lambda are free lambda modules, then the cup product map that we just defined from H star X lambda tensor H star Y lambda to, well, where does it go? It goes to H star X times Y. Well, the box tensor product of lambda with lambda is just lambda. So it goes to this. Then this is an isomorphism of graded rings even. Well, let's just say graded groups for now. But if you think for a little bit, you'll see that so we define the cup product. So I claim these things are actually rings now. So let me just let me say a word about that. So what is the ring structure here, since we can define it? So well, there's a map H star of X lambda to tensor itself to H star of X times X lambda, right? So we've just made that. That's the cup product, and now we can pull back via the diagonal map. Okay, and again, it's not totally trivial that this is actually a ring map, but you can check it in check cohomology, for example. In fact, it's formal from the properties of the cup product, but we haven't really developed those properties yet. Great. So this says that we have a sequence of graded rings under this weird condition that we have free lambda modules. So let me make that the cohomology is free. So the reason we need that is that last time we kind of gave the fancy formulation of Kunneth, and if it had some torque.
I think it cut out again.
Terms. Okay, and then there's.
I think you cut out again.
Oh, I said. So this. Oh, can you hear me now?
Yeah.
Yep. Yeah. So this assumption that one of the cohomology rings is free as a lambda module makes all those Tor terms 0. So those Tor terms always vanish if we use QL cohomology. So we defined that a couple class periods ago. So if we have a ZL sheaf, we get a QL sheaf, and the definition of the cohomology is you take the cohomology of the ZL sheaf, which was some inverse limit, and you tensor with QL. So the statement again is if X, Y are as above. So if they're proper, then H star of X QL tensored with H star of Y QL. Now we have this cup product map to H star of X times Y. So as above just means proper, by the way. So no assumption on freeness now. H of star of X times Y QL is an isomorphism of graded rings. Okay, and if you've seen the cup product in singular cohomology, you can probably guess a lot of the properties of this isomorphism and of the ring structure. So for example, these rings are graded commutative, but we're not going to talk about that. All right, so this is I think the sort of concrete formulation of the Kunneth formula. And ultimately in the end, for most, I mean, I really like but ultimately for applications to point counting and the Weil conjectures and stuff.
You cut out again when you said, I really like.
Oh, great. So what I was saying is I really like these sorts of integral situations, like thinking about the integral structure on analytic cohomology. But ultimately for the applications in this course, like for example, for the Weil conjectures, we only actually care about QL cohomology. So this sort of simpler situation will actually be all we care about. Maybe let me, maybe I'll delay that remark till later. Okay, so let me sketch the proof. So let me sketch let me just remind you now what the fancy version of Kunneth was. So the fancy version of Kunneth, and I'll sketch the proof of that. So X, Y were proper K schemes. F was a sheaf on X Etale, which was constructible, and same with G. And K was algebraically closed. Then the statement was that then there was an isomorphism as follows. So this sort of so there was an isomorphism, a quasi-isomorphism of complexes. And here there should be some L's here, an L here, if you'd like. So this is in the category of bounded complexes of abelian, the derived category of bounded complexes of abelian groups. Okay, so let me just remind you what this is saying. So what that means is that what is this R gamma X Etale F? This is a complex whose cohomology computes the Etale cohomology of X Etale with coefficients in F. So for example, one way to get such a complex is you take an injective solution of F and you take its global sections. And so this R gamma is the quasi-isomorphism class of that complex. And then the statement is that, well, if you look in the category of complexes where you've inverted quasi-isomorphisms, there's a map like this, which is a quasi-isomorphism. And okay, there's more content. So the ultimate content is that this map is it's like a canonical map. So okay, I mean, I can actually state it rigorously. It's in the case where X Etale and Y Etale are like quasi-projective. So in the case is where check cohomology computes derived functor cohomology. So in that case, these complexes are gamma. You can just write as you take the check complexes for your cover, and you take the direct limit over all covers. That's some complex whose cohomology computes R gamma X Etale F. The proof that check cohomology computes derived functor cohomology, in fact, implies that that complex is quasi-isomorphic to the one with injectives. So here what you can do is you can take these R gammas to be the check complexes, and then this map to be the cup product. So this map is the cup product that we just described. So that's at least a rigorous formulation of this statement in the case where X, Y are at least projective, say, rather than proper. So I can at least, without too much, without any real derived category nonsense, we can actually state a rigorous version. Okay, so I'm just going to sketch the proof because it's a little involved. Are there any questions before I begin? E should be in Y Etale. Yeah, that's right. And I wrote and Robert. Yeah, so I wrote K is K bar here. So it's enough to be. I mean, algebraically closed implies separately closed, but yeah, Robert, it's enough to be. It's enough to be separately closed. That's right. Does that answer your question?
Yes, thanks.
Great. And maybe just a remark, I mean, we could have seen something like that was necessary. So for example, if you take K to be a field with interesting Galois cohomology, like Q, then it's sort of not so hard to see that Kunneth is false. Right. So if you just take both X and Y to be spec Q, then X times Y is also spec Q. And yeah, if you can compute these groups using class field theory, for example, and you'll see that the statement would be false. Okay. Are there any other questions before we get started sketching the proof? Maybe actually before I do the proof sketch, let me just give one example since Arvind asked for some examples. So an example. So let's just take a curve. So let's just compute now the cohomology of a curve C times P1. Let's say with QL coefficients. So can anyone tell me what this is going to be? So here, let's say suppose C is a smooth proper curve. Any thoughts? So, okay, so what is H star of C? Well, we worked out what it is with Z mod L to the NZ coefficients. Taking the inverse limit over N, we get, well, we get QL here for star equals 0. So we get ZL with ZL coefficients, and then tensor with QL gives you QL. You get QL of -1 for star equals 2. And here you get, if you'd like, the L-adic Tate module of the Jacobian twisted by -1 for star equals 1. So here, how do you see this? You just compute this with mu L to the n coefficients instead of ZL to the n, and then tensor by the dual of mu L to the n, which gives you this -1 factor.
What is VL?
So here VL, so VL is the Tate module of the Jacobian.
Tensored with QL?
Yeah, that's right. Sorry. Sorry, I can never remember what notation is standard. So yeah, so this is it's the rational Tate module is what people call this.
Yeah, it seems to be standard.
All right. So then H star of P1. So here, this is, by the way, this is over K in algebraically closed field. So H star of P1 with QL coefficients is just, well, it's we just write it down because P1 is a curve, but it's QL for star equals 0, 0 for star equals 1, and QL of -1 for star equals 2. So now what does that tell us about the product? So we can just work it out. So we just take this and we take it, and then we also take it shifted by QL of -1, right? In degree 2. So we get QL in degree 0. We get the Tate module of the Jacobian of C -1 in degree 0 in degree 1. Then in degree 2, interesting things start happening. So we get what do we get? So we get QL of -1, direct sum QL of -1, right? Because we get something from this tensor this, and this tensor this. So we get 2 copies of this. Then in degree 3, we get VL of the Jacobian of C twisted by -2. This is 3. And then in degree 4, we get QL of -2. So this is the first surface for which we've computed the L-adic cohomology, except insofar as last time I sketched how you would compute the cohomology of a liftable variety. So we could have used that. So this is kind of like a typical application of Kunneth. And am I cutting in and out? My computer just
you're back up.
Oh, sorry about this, guys. Well, was this computational reasonably? Was it followable?
Yeah.
Great.
Yep. I'm assuming the recording should be not cut out.
We'll see. I mean, it's recording to the cloud, so it's not so clear.
Okay.
Yeah, we'll see. Okay. Great. Okay, so now let me skip proof. All right, so step 1 is the projection formula. So basically what we're going to do is we're going to try to use the Lauré special sequence. So we want to compute something on x times y. We can compute that by projecting to x and then projecting to the point, right? So that's what the Lauré special sequence is about. But we're going to do that kind of in the derived category because I think that makes the description a little bit more clean. I mean, we could try to do it with spectral sequences, but it would be really rough because you'd have to keep.
Can I ask?
I'm sorry.
Just as a big picture, like what do we gain by computing these cohomology groups? Like what do I know about the variety if I know that H1?
Like in this case?
Yeah, for instance.
Yeah, that's a good question. I mean, so the first thing you know is, well, you can do point counts. That's not so exciting for C times P1 because a point of C times P1 is like a point of C and a point of P1, right?
Mm-hmm.
So I mean, for a product like this, I would say you don't gain that much. That might happen is you might, I mean, so like when does this actually come up? So suppose you have a sheaf on, so here we have the cohomology of x times y. So suppose you have a sheaf on y and you want to make a sheaf on x. So a common situation where you might want to do that is where maybe x equals y, and you're trying to convolve with some sheaf on the product. So what you'll do is you'll pull back to y and push forward to x. And when you do that, you'll often have to compute some things on the product. I mean, that's sort of how it will show up for us. But I don't know. I mean, what do you gain? Like you've gained a big new class of varieties whose cohomology you can compute, which is
no. I think maybe I didn't phrase it correctly. I meant in general for any variety, what do you gain by computing the QL?
Oh, I see. So the main thing is point counts, at least from the point of view of this course, right? So computing the QL cohomology by the Lefschetz fixed point formula, which we'll talk about in a couple of class periods, tells you the number of rational points. So for a finite field, so that's the main
over finite fields. Then you're saying.
Yeah. In general, I mean, so these. Those Galois representations, at least. Oh my God, maybe I should cancel class. Yeah, so these groups carry Galois representations just because of the functoriality of L-adic cohomology.
Okay.
Right. So how do you suppose? Let me actually. I mean, it's important to know this. So maybe let me write something. So okay. So what info? I appreciate you guys asking this question, but it does. So the question is, what info does H star of x k bar Etale QL carry? So first of all, over finite fields, it carries point counts. We're going to talk about that that soon. So in general, let's say K, which is a fully generated field, the Galois representations on these groups conjecturally carry a lot of information. So if I get to cycle classes by the end of the day, we'll see some of that. So they conjecturally carry geometric information. So for example, the Tate conjecture tells you that you should be able to read off, for example, the rank of the Néron-Savary group from these Galois representations. But in fact, you're supposed to be able to read off like a huge amount of cycle theoretic information. So that's one application. But I mean, okay, like why do you compute cohomology in general? It's because it's like an in principle computable invariant of a variety. And so like the geometric properties of the variety that you're trying to study, well, maybe they'll be reflected in L-adic cohomology and maybe they won't. But like, for example, there are birational invariants that you can extract from L-adic cohomology. Like that's why we do cohomology in general, is because it's like a more computable linear algebraic invariant of a variety, which is hopefully like reflecting some geometric questions you're interested in. Does that help, Arvind?
Yeah, thanks. I think these are two solid motivations for me to care about it. Thanks.
Yeah. So for example, yeah, I think I guess for you've thought about some rationality questions, right? So one thing is the eigenvalues of the valuations of the eigenvalues of Frobenius on L-adic cohomology. So like the p-adic valuations carry some birational information. Yeah. Okay. So yeah, maybe let me just give one very concrete example. So if C is an elliptic curve, this thing is this degree 1 cohomology is more or less the ellatic Tate module. It's dual to the ellatic Tate module, and that I think you know. Singular, like more geometric information too. Yeah. Okay. Let me sketch the proof of Kunneth now. So step 1 is the following claim, which we've already actually used a little bit implicitly, but I want to make it explicit. So suppose f from x to s is a map. Suppose f is a. I'm gonna prove it for ZL sheaves. So f is a flat ZL sheaf on x Etale, which again does not mean a sheaf on x Etale. It means an inverse system of such things. And G is a bounded above complex of abelian sheaves on S. Then the claim is that there's a natural morphism going from the derived push forward of F. So just a reminder, so what is this thing? This is you take an injective resolution of F and you push it forward. And the claim is that there's a natural quasi-isomorphism as follows to F lower star of F tensor F upper star of G, which is a quasi-isomorphism. Okay, so what's the idea of this? So if G is just ZL, well, then this is the identity map. Right, so if G is just ZL, so what is this? Well, this is RF lower star of F, and this is ZL, so this is also RF lower star of F, right? And now there's a series of reductions, but the idea is to reduce to this case. So in particular, this tells you what to do if G is a complex of flat ZL sheaves. So you need to do a little work. So you need to reduce to the case of actually torsion sheaves, and then work with the case where G is like the constant sheaf Z mod L to the N. So that's the case of so-called perfect complexes, and then there's a fairly involved reduction to that case. Yeah. But I don't want to say much about this. But let me just remark. So we've already seen an example of this claim. So we've seen the following. So we've seen, for example, that HI of X with mu L coefficients is canonically isomorphic to HI of X with Z mod L coefficients tensored with mu L. So we've used this a lot when we've computed. Okay, and this is not so hard to see. I mean, what did we do? Like over the algebraic closure, we like picked an isomorphism between mu L and Z. Sorry, this should be over an algebraic closed field. So here, but this is an isomorphism of Galois representations. So what did we do? We like picked an isomorphism between mu L and Z mod L, so namely a choice of L roots of unity, and then we thought a little bit about what Galois did, like how it moved that isomorphism around, and well, what does it do? It moves the root of unity. So this is the case. So this is the case. This is the case where F is the constant sheaf Z mod LZ, and G is the constant is mu L. So why is that? Well, this is the right hand side of our formula, and this is the left hand side. Right. So F star of G tensored with Z mod LZ is just the sheaf mu L on X Etale, right? And taking cohomology is taking this R F lower star. So this is the case where F is Z mod L, G is mu L, and F is the structure of the map. So the map from XK bar to spec K bar. Okay, so I'm not going to prove it. It's quite involved. Okay, so but given that, we can do the proof. So now we're gonna see where we need properness. So we're gonna consider the following diagram. So we have x times y. This goes to x. This goes to y. I'm gonna call this P and this Q, and these both map to a point. So to spec k bar. Let's call this F, and let's call this G, and let's call this composite map H. Great. And I'm going to assume that F and G, recall, are now. So I sketched this for ZL sheaves. Really, everything I said works for Z mod L to the n. So this works also for flat ZL or Z mod L to the n sheaves. So I'm gonna now work in the torsion setting. So FG are going to be constructible sheaves of Z mod L to the n Z modules.
And in those cases, F is just actually flat, right? No.
Sorry, say that again?
So, and in the Z mod L.
Yeah, then F is a sheaf of free Z mod L to the n Z modules, yeah.
Okay.
Yeah. So a flat constructible sheaf of Z mod L to the n Z modules is a sheaf of free Z. It's a sheaf of free Z mod L to the n Z modules. So constructible sheaf of Z mod L to the n Z modules, and I'm going to as before, I'm going to assume. I mean, you don't actually need that, by the way. If you replace these tensor products with derived tensor products, you don't need flatness. Yeah. So I'm just going to assume that F is a sheaf of flat Z mod L to the n Z modules. So this is a simplifying assumption. So if you put the derived tensor product here, you can ignore it. So then what are we trying to compute? Well, we're going to try to compute our F lower star F tensored with our G lower star of G. So here we have F living on X and G living on Y. And we're trying to compute this tensor product. So what is this? So this is just a complex computing the cohomology of F, and this is a complex computing the cohomology of G. That's the first term of the Kunneth formula, right? So what we're going to try to do is we're going to try to compute this using the projection formula. So this is going to be isomorphic by the projection formula to the following thing. So it's going to be our F lower star of F tensored with F upper star our G lower star of G. So this is the projection formula. So here we're using the assumption that F is flat, or we have to put an L here, which won't affect the argument at all. So what does the projection formula let us do? It says if we're taking the cohomology of F tensored with something pulled back from the base, then we can just pull that thing out, which is accepted. So this situation where we pull something, where we take a push forward and then pull it back, if this map G is proper, which it is by assumption, then we can compute that by going around the other way, right? So this F upper star of R G lower star of G, we can compute as P lower star or as RP lower star of Q upper star of G. So now proper base change gives us the following. It gives us that this is RF lower star of F of let's see, we took our P lower star of Q upper star of G. So this is just proper base change applied to this inner term F upper star of R G lower star. Great. Okay, so now Now this is again the kind of thing where you can apply the projection formula. So here we're taking f tensored, so something on x tensored with the push forward to x, and that's the sort of situation where you can apply the projection formula. So this is the same by the projection formula as our let's see, our f lower star of what do we get? We get our p lower star of the box tensor product of f box G. Let me actually write it out, of p upward star f tensored with q upward star G. So all I did is rewrite this inner term using the projection formula. Okay, and now we're done. What is f composed with p? It's just the structure map H, right? So now this is the same. Sorry, these are all isomorphisms. This is the same as our H lower star, which is also known as our gamma of Are there any questions about that? So this is the end of the proof. So a couple of remarks is we actually see that we don't really need anything. We don't really need that much. So this works for S. This works for there's no hypotheses on S. So this works for arbitrary S. So when I say S, I mean the base. So let's call this S. Arbitrary S. So in particular, Robert asked earlier if there's an analog of Kunneth over Bob asked earlier if there's an analog of Kunneth over non-algebraic closed fields, and there is. But what it is it's you get a statement about sheaves on spec K, which are not just vector spaces; they're vector spaces with Geller representations. So what you would get is some isomorphism of complexes of sheaves on spec K, or complexes of Geller representations. So it would be a little more complicated. In particular, if you tried to make it look explicit, what you would get is you'd get some kind of special sequence involving Geller cohomology. Okay, so a couple other remarks. So we didn't need properness everywhere. So for example, it would have been enough to excuse me. So it would have been enough to have G proper is enough. So one of these things being proper is enough.
Sorry, what have you written? It works for any what S?
So any arbitrary base S. So here I said
okay.
But put any spec here. So we could have also assumed that just G was proper, or we could have assumed that L was invertible on S, which gives us good finiteness properties for these push forwards, and F was smooth. So then instead of using proper base change here, we would have used smooth base change for F, and then that requires some finiteness conditions, which would be guaranteed if G was a sheaf of Z mod L to the n Z modules where L was invertible on the base. So there are a few other cases where we get Kunneth formulas like this. And so just to keep in mind, sort of the non-example that will cause problems is the case where you take the affine line and take FP cohomology, and then the claim is that the cohomology of A2 is not the tensor product of two copies of the cohomology of A1. All right, are there any questions about that? Has the connection been okay for the last little bit?
Yeah.
Mm-hmm. As you said that.
What just happened?
The moment
as you asked that, it cut out.
All right, so
Otherwise it was fine.
Ask, I guess, but it was okay during the proof.
Yeah.
All right, so now I want to start talking about cycle class maps, which are really almost the last topic before Poincare duality and the Lefschetz fixed point formula. Okay, so what are cycle class maps? So I'm going to assume that so X is going to be a non-singular variety throughout, so non-singular variety over K, which is a field of characteristic. So this is a field of characteristic P not equal to L. So I want to define a cycle class map. So this is supposed to be the L-adic analog of integration along a cycle. So in particular, over the complex numbers, if you have a smooth projective variety and a cycle of codimension R, you can integrate. So let's say a cycle of, so you have a subvariety, let's say of dimension maybe D, dimension D. So you can integrate a 2D form over that, right? Because a subvariety of complex dimension D is real dimension 2D, and now you pull back your 2D form to it and you integrate. At least if it's smooth, that's something you can do. You can even do it if it's not smooth, if you think a little bit. So that gives you a functional on de Rham cohomology in degree 2D, right? But de Rham cohomology satisfies some kind of Poincare duality. So that's the same as an element. So a functional on de Rham cohomology in degree 2D is the same as an element of de Rham cohomology in degree 2 dim x minus 2D, right? So that has so I just described for you in de Rham cohomology how to associate an element of de Rham cohomology to a subvariety of your variety. So we're going to do that now in L-adic cohomology. So I'm going to let so CR of X is going to be the free abelian group on prime cycles. So that just means irreducible subvarieties of codimension R. So if you've any subvariety, you can associate it. Sorry, if you have any subscheme of pure codimension R, you can associate to it an element of this. You have to make sense of multiplicity, but let me ignore that for now. And so our goal will be to define a cycle class map, a map which we'll call col for class, from CR of X to H2R of X with coefficients in lambda twisted by R, where here lambda is going to be either Z mod L to the NZ or ZL or QL. Okay. Excuse me. So, and this map will be functorial and satisfy other good properties. So let me call this maybe col R. It'll satisfy some other good properties, and in particular, col 1 we know how to write down. So col 1 will be a map from codimension 1 cycles in X to H2R, sorry, H2 of X lambda twisted by 1. So that's just if lambda was Z mod L to the NZ, this is just mu L to the NZ. So can anyone tell me what this is going to be? So I claim we've already seen this.
Is this going to come from the exact sequence we had on GM or? Yeah,
exactly. It's going to come from the Kummer map. So this C1 of X maps to pick of X, which is just the same as H1 of X GM. So let me actually just set lambda equal to Z mod L to the N and Z, since it suffices to do that case. So there's a natural map from codimension 1 cycles to line bundles. So hopefully you've seen that explicitly. What is it? It's you send a, well, maybe one of you, well, explicitly, what is it?
Is it connecting homomorphism?
So the map from C1 to pick X.
Oh, I see.
Yeah, so how do you associate to a codimension 1 cycle a line bundle?
Just take D and set it to O of D.
What is O of D?
You just count like where like the number of times it vanishes.
Mm-hmm.
Like
Yeah, so another way of saying that is you send it a cycle to the dual of its ideal sheaf, right?
Mm-hmm.
Yeah. So you said this sends, as Lester says, you send D to O of D, or you send a cycle to the dual of its ideal sheaf, and then you extend by linearity. Okay, and then there's a map to this thing, which is the Kummer map. And let me just remind you, so what is that? So we have 1 to mu L to the N to GM to 1. So where this is taking L to the nth powers, and that induces a map from, so that induces a map to, so this is just mu L to the N. So the boundary homomorphism here is a map from H1 of GM to coefficients to H2 with coefficients in mu L to the N. So we already know what H1 is. Great. All right. Are there any questions about that? All right. So let me now say what to do. So let me say what to do. So the definition. So for Z non-singular of codimension R, I'm going to define col R of Z to be as follows. So you take the image of 1 in, I'll say what I mean by this in a second, in H, excuse me. Oh my God, sorry. I'm just having a little bit of a, with coefficients in lambda. So this maps to H2R of X supported in Z with coefficients in lambda of R. So this is an isomorphism, right, by purity. And then this maps, well, if you have a section of X, a section of a sheaf on X supported at Z, that gives you a section of X. And that, so we get a map from H2R with supports on Z to H2R of X with coefficients in lambda R. So this is the class of Z, and then we extend by linearity. All right. So here this isomorphism was the key input. This is purity. All right. Are there any questions about that? Okay, so then what about for non-singular Z? So the lemma, which maybe I'll say a word about the proof of. So the lemma is that let's suppose Z inside of X has codimension R. Now with no non-singularity assumption, then, well, the cohomology with supports on Z still looks very, very close to what it does for non-singular Z. So first of all, HS with supports on Z of X with coefficients in lambda is 0 for S less than 2R. And moreover, or over H. So the in degree 2R, what happens, so the cohomology with supports on Z of lambda is the same as the cohomology with supports on Z minus its singular locus of X minus the singular locus of Z with coefficients in lambda. Okay, and now here, so Z minus Z sing inside of X minus Z sing is a smooth pair. Okay, and I won't say much about the proof. So what I'll just say is that the proof is an induction on the dimension of Z and
you cut out again.
So you delete those. I'm really sorry, you guys. This is very annoying. Anyway, I was just saying the proof is you filter by the single locus. So that's and I don't want to get into it, is that there's another long exact sequence of involving cohomology with supports, which we'll never use again in this course, and it would take another 40 minutes or something. This is this, and then here you actually have a smooth pair once you delete the singular locus of Z. So now you can just use purity. Okay, so now once you have that, well, I've defined the cycle class for prime cycles. So now you get Cole by extending it by. Okay, so let me just make a couple remarks here. So unfortunately, Arvind is gone, but this is closely related to his question. So we get this map, Cole, from codimension R cycles on X to H2R of X with coefficients in, and so this map is Galois, just from construction, the map is Galois equivariant. So maybe let me go up to K bar or something to Galois equivariant. Right, so what does that tell us? So what that tells us is that we have a cycle over K. So a cycle over K, meaning like the defining equations, for example, of coefficients in K, this maps into H2R of xk bar and then the Galois invariance. Just because if you're defined over K, well, you're Galois fixed here, so you better be Galois fixed here. So the conjecture, the Tate conjecture, or at least part of the Tate conjecture, so let's suppose X is smooth and projective over K, which is a finitely generated field. So finitely generated field just means you take the fraction field of a variety over FQ. So for example, you could take a number field or FQ. In this situation, R cycles on X tensored with QL to H2R. Oops, I don't know what happened there. And erased what I'd written. So the conjecture is that, can you guys hear me, by the way?
It's cutting in and out.
can hear you.
I'm really
Right?
sorry.
Yeah.
Or never mind.
Sorry, say that again.
Now everyone's cutting out.
I think you're good now.
Yeah, we're good.
Let's see what happens. So we have this map from the QL twisted by R, and then Galois invariance. So the conjecture is that this is surjective. So meaning that if all cycles have to land in here, so the conjecture is that if a class comes from a cycle, could come from a cycle, then it does come from a cycle. And maybe note, I mean, this is really a rational conjecture. So if you just put ZL here, this would be false. There's known counterexamples, and it's not so hard to make them. Although I think there's no known counterexamples with R equals 1, maybe. And if you put Z mod L to the end here, it's super false. Like in that case, there are, I think, examples if you take like Z mod L. Okay, so this is the conjecture. This is like one of the most important open conjectures in mathematics, in my view. And so this is in my view the fundamental way that analytic cohomology. So let me maybe make some remarks about this. So here's some kind of example. So let's suppose we have X and Y. And so let's look at H star of X times Y. Coefficients and let's look at H2n of X cross Y. So this is the middle cohomology of X cross Y with coefficients in QL of n. Suppose that the Galois invariance of this. So another way of saying this, if you think about the Kunneth formula, is that there's a map from the cohomology of like a Galois invariant map from the cohomology of X to the cohomology of Y, which is not. So it's the same statement. So then this should imply that there exists a cycle on X times Y, with non-trivial cycle class. So suppose we have alpha in here. So non-trivial cycle class alpha, here up to some kind of QL linear combination. So in particular, if you think of this alpha as like a map on cohomology, then which I haven't quite told you how to do yet. It's the easiest way. We'll use Poincare duality, so we'll see it soon. Then the statement is that that map is somehow induced by a cycle. So the sort of canonical examples X and Y to be abelian varieties. So that's well, over finite fields, Tate proved this, and over finitely generated fields in general, it's due to faultings. So if X and Y are abelian varieties, this is saying that any map between analytic Tate modules actually comes from a map of abelian varieties. And that's a very concrete way that somehow, well, Tate modules are an example of analytic cohomology, like reflect the geometry of the underlying variety. Are there any questions about that? Okay, so next time, so the reason I had to introduce Kunneth was that I want to talk about Chern classes next time, and those will use a little bit of Kunneth. So I want to talk about Chern classes, which are another POV on cycle classes, if you'd like. So I'll quickly go through that, and then we'll talk a little bit about Poincare duality and Lefschetz. All right. Are there any questions about that, or anything else we discussed today?
Are there any like sort of rationality sort of conditions, like or like sort of equivalence relations you can put on the cycles so that like they have the this map factors.
Yeah. So
map factors
cycles modulo rational equivalence. It also factors through cycles modulo algebraic equivalence. If you put this QL here, or in general, in fact, if you're over an algebraically closed field. So there's sort of the what you can do, of course, is you can mod out by the kernel of this map, right? And it obviously passes through that quotient, and that also has a name. It's called homological equivalence. But there's like a very sort of jarring open conjecture, which is that the kernel of this map. So if you take the kernel of this map and kind of intersect with CR of X, so sorry, take the kernel of like this map where lambda is QL. So that's some subgroup of this group, right? And the conjecture is that should be at least rationally independent of L. Meaning if you take that kernel and then tensor with Q, that's supposed to be independent of L. And that's very open.
Is that one of the Grothendieck?
Let me stop recording.
Is that one of the Grothendieck things? Like
it's
one
like
of the
it's like
conjectures?
it's a conjecture of Grothendieck. I don't remember if it's one of the standard conjecture. Maybe it's the homological standard conjecture or something. Yeah, that's a good. All right, I'm going to stop recording. I'll stick around for a couple minutes if anyone has any other questions, and I'll see you on Monday for office hours, if not.